Hello there, and welcome to the next video in our Essential Skills series. These videos are to help you as you prepare for paper 1, the physics paper, by focusing on the skills rather than the content. I'm Dr. Derek Fish, Director of Unizulu Science Centre at the University of Zululand. This next video deals with multiple choice questions and a particular type of question we shall call a ratio question. You can find this in your booklets on pages 66 to 70. But before we go to those pages, let's start at the beginning again and just see how it fits into your exam. So let's have a look at page 3. Remember to check the bottom right-hand corner of my screen to see the page number, which of course is in the top right-hand corner of your page. So here is your contents page on page 3. We're now looking right at the bottom on multiple choice and ratio questions. How to answer multiple choice questions generally, and particular this type of question we will call a ratio question. Now, where does this fit into the curriculum? Well, it's a bit like equations in that it fits in everywhere. Multiple choice questions and ratio questions can come out of the mechanics section, out of the wave, sound, and light section, out of the electricity and magnetism section, or out of the matter and materials section, the photoelectric effect. So in terms of curriculum, you need to know all of it. Please don't forget the grade 10 and 11 work. And again, a comment from the examiner in the yellow box that grade 10 and 11 work was poorly understood and needs to be integrated with grade 12 work. In terms of marks breakdown, this is the breakdown of the paper, and multiple choice will always be question 1 for 20 marks. So question 1 is always multiple choice for 20 marks. And the distribution of multiple choice questions will be similar to the distribution of topics in the longer questions. Multiple choice is 10 questions for 20 marks. So you need to work at about 2 minutes per question. Again, always 20 marks for question 1. Where will multiple choice and ratio questions come from? Well, multiple choice can come from all of these subject areas and probably will. But in the papers I've looked at, we've had ratio questions from Newton's laws, projectile motion, momentum, energy, electrostatics, electric circuits, and the photoelectric effect. And we'll look at many of those questions at the end of this video. Special skills on page 5. Well, of course, all curriculum skills are important, but particularly these: scientific notation, make sure you can use it on your calculator, conversion of units, especially changing the subject of the formula. In fact, we're going to look at an example with Ohm's law just now. Fractions and ratios, rate and direct and inverse proportion. Again, you see the example there that I is directly proportional to V, but inversely proportional to R. More on that in just a moment. So let's look at multiple choice questions, and let's have a look at your top 10 tips to master multiple choice questions. Now, you need to get lots of practice looking at multiple choice questions from previous exam papers, but it's difficult for me, except for ratio questions, to talk about a general strategy because the questions are always difficult. And I know that many of you look at question 1 and you think that multiple choice questions are impossible, terrible, terrifying, or all of the above. But they don't have to be. And here are some general tips which can help you. Number 1, please read the entire question. Don't jump to the answer before you've finished reading it. Number 2, try to answer it in your mind first, if possible, covering up the answers. If you get to the right answer in your mind, then you can choose one from A to D to simply confirm your correct answer. Number 3, eliminate any clearly wrong answers. If nothing else, this will just narrow the odds for when you have to guess. Number 4, select the best answer. I know sometimes pupils say I left it blank because none of them was perfect. Don't worry about that. Select the best answer. Number 5, find the relevant equation from your data sheets. We'll talk a bit more about this, but this is really important. And very often, the solution to solving a multiple choice question, and especially the ratio type questions, comes from finding and using correctly the equation from the data sheets. Number 6, look out for key words. Beware of a word like not, which changes the question to negative. Look out for sometimes, always, and never. Number 7, make sure you know the difference between all of the above and none of the above, which are two very different things. Number 8, never, ever, ever leave it blank. We don't have negative marking at school, so take advantage of that. If you really don't know, close your eyes, take your pen and take a stab and choose one from A to D. So guess if you have to, but before you guess, make sure it's an educated guess. And you can see number 3, if you've eliminated clearly wrong answers, you're much more likely to get to the right answer. And finally, just a tip that the correct answer often, but not always, contains more information. Now, again, a comment from the examiner. Multiple choice is one of the weakest sections. Learners need practice. These tips are great. They're not in your booklets, so pause the video and take a note of them here if you want to. Let's jump to our data sheets on page 38 to 40. And remember, these are really important. Now, I hope by now you've watched video 6.1, which is an introduction to equations. We went through the data sheets in great detail. I'm not going to do that again. But just to remind you, the data sheets are very nicely laid out. They have headings, and the motion equations will probably be used mostly in projectile motion. The force equations could be used in question 2 on Newton's laws or question 4 on momentum. Further down on page 38, work, energy, and power equations will be used in question 5. Wave, sound, and light will be used in question 6, the Doppler, or these ones, question 10, the photoelectric effect. Turning over to page 39, electrostatics equations belong to question 7. Electric circuits to question 8 on circuits and internal resistance. And on the bottom of page 39, you have the equations for question 9 on electrodynamics and alternating current. On page 40, you have your constants. These are not as important for multiple choice, and particularly not for ratio questions, where you'll see that we tend to combine and ignore the constants. But nevertheless, for all longer questions, it's important to know which constants to use when. And here's a guide, which I gave you in video 6.1 on how that works. So let's take a look at these ratio questions, a special example of multiple choice questions, which can be found on page 66 in your books. Before we actually get into those, let's again use a great PHET simulation just to look at this idea of ratio questions, and particularly direct and inverse proportion. This one is called Ohm's law, and again, teachers, you have it in your teacher pack. Please explore it by yourselves and with your class. The idea of this is really just to show direct and inverse proportion. For Ohm's law, V equals IR. Of course, this is better written as I equals V over R to show that current is directly proportional to voltage and inversely proportional to resistance. So here we are actually in the simulation. This is not a screenshot anymore. We have a simple circuit, batteries and a resistor, and you can make the voltage bigger by adding batteries or smaller by taking batteries away. Similarly, you can make the resistance higher or you can make the resistance lower. And the size of the symbols here, V, I, and R, give you an indication of how big that quantity is. Now, I is the dependent variable. So let's see how I depends on V. If we make V bigger, we see that I increases at the same time. So I is directly proportional to V. They grow and they shrink at the same time. What about R? I is inversely proportional to R. If I make R bigger, I get smaller. If I make R smaller, I gets bigger. So that's an example of inverse proportion. So as always, this PHET sim is a great way to get to know the subject. So on page 66, let's look at these ratio questions. Multiple choice often involve ratio calculations, which are in terms of an unknown quantity rather than a numerical value. So the answer will not be a number, and you can see the possible answers here. Let's look at a typical question from the November 2014 exam paper. It says the magnitude of the gravitational force exerted by one body on another is F. When the distance between the centers of the two bodies is doubled, what happens to the magnitude of the gravitational force in terms of F the original force. So they didn't give you this picture, but you could say that the gravity that the Earth exerts on the moon is F when they're distance r apart. If the moon went much further away, so that they were distance 2r apart, what would become the size of the gravitational pull that the Earth exerts on the moon? Now, you might want to think about this a little bit, but because Newton's law of gravitation shows that gravity is inversely proportional to r, we actually get a correct answer of 1/4 F here. Now, if you're not sure how I got that answer, then watch closely because we'll go through this method carefully. Now, you notice what we did is we used some of our top tips for multiple choice questions, which I taught you just a few minutes ago. Not all of them, but read the entire question, tried to answer it in our mind without looking at the answers, selected the best answer, which is A. We did this by finding the relevant equation from the data sheets. We'll do a lot more about that. We never leave the answer blank, and if necessary, we make an educated guess. So there's a very systematic 4-part method given to you on page 66. So if you're not sure how we got answer A, let's go through it together. Step number 1, identify the correct equation for the relationship in the question. Now, the relationship is gravity between two bodies. So on page 38, the first page of data sheets, we choose Newton's law of universal gravitation, and that's the correct equation. Secondly, remove all the variables that are not mentioned in the question. Now, the question says nothing about the masses changing, so remove them and make these and the existing constants like g into one constant term, k. So we rewrite the law of universal gravitation to say that only the radius, the distance between the bodies, is going to make any difference. Then substitute the new value for the variable which changed. R becomes 2r. Make sure to put it in a bracket before you square, because the r and the 2 must be squared. Simplify the new equation. F equals k over 4r squared when you square the bracket. That's equal to 1/4 times k over r squared, which was our original value of f. So that's 1/4 f. So the answer is A. Now again, a great way to investigate this is another PHET simulation. It's called Gravity Force Lab Basics. Let's have a look at that. So here we are on the real simulation, not a screenshot. Again, teachers, this is in your teacher pack, so please do take time to explore it by yourself and with your students. So we have two massive bodies, 6 billion kilograms and 4 billion kilograms, and we can see the force they exert on each other, both by the number and by the size of the arrow there. We can also see the distance between the centers of the bodies, which is presently 2 kilometers. Now, I can increase the mass of mass 1, and you can see that the force gets bigger, both by the number and the arrow. If I make it smaller, the force gets smaller. So clearly, the force is directly proportional to mass 1. Similar for mass 2, if it gets smaller, the force gets smaller. If it gets bigger, the force gets bigger. So it's directly proportional to mass 2. When we look at the distance apart, we see something different. When they get further apart, when we increase the distance, the force gets dramatically smaller. When we decrease the distance, the force gets much bigger. So let's do an accurate calculation. At the moment, they are 2 kilometers apart. Without changing the masses, let me double the distance between them, like in the question on page 66. So notice the force is just about 400 newtons. If I double the distance between them to 4 kilometers, the force becomes 100 newtons. Can you see this is 1/4 of what it was previously? If I halve the distance, the force becomes 4 times as much. So I think you can see these relationships very nicely on this PHET simulation. Now that was really quite a simple question. Let's look at something a little bit more difficult on the bottom half of page 66. So the same question, but now I've said the distance between the centers is halved and the mass of one body is halved. So instead of doubling the distance, we've halved it. Now you should know as they come closer, the force should get stronger. And the mass of one body is halved, but that should have the effect of making the force less. So what is the combined effect on the magnitude of the gravitational force, again in terms of the original force F. So we use exactly the same method as in the top half of the page. Number one, identify the correct equation for the relationship in the question. Again, it's Newton's law of gravitation. Number two, remove all the variables not mentioned in the question. Well, that's just the second mass, and make these an existing constant g into one constant term. So we can rewrite the equation as force equals k times mass 1 over r squared. We need to keep these two variables in because they're both going to change. Then substitute the new value for the variable. So r became half r, keep it in brackets, and m1 became half m1, again, keep it in brackets. Now simplify. Half r all squared becomes a quarter r squared, half m1. Simplify, you can do it yourself, and you'll get the new force is equal to 2k m1 over r squared, which you can see is twice what it was originally. So that's 2 times the force. So the correct answer is option C. And you can see that's a little bit more difficult. Of course, as you get some practice, you might not need to go through all these 4 steps every time. But while you're learning this method, I think it could be very useful for you. At the top of page 67 is a general table, which is a summary of the effect on the gravitational force by changing the masses on the left and changing the distances on the right. Please take time to study that. Make sure that you understand each of these examples here. Now, of course, the best way to understand this table, and indeed to understand any part of physics, is to get some practice yourself. And we're going to do that with an exercise on the bottom of page 67. Now, this exercise uses Coulomb's law of electrostatic attraction or repulsion instead of the gravitational law. But the structure of the equation is exactly the same as what it was before. And you can see F equals k q1 q2 over r squared. It's exactly the same structure as the law of universal gravitation. So once again, let's have a look at a PHET sim. The sim is called Coulomb's law, and again is in your teacher pack. So here we are with the real live simulation. And of course, the difference with electrostatic force is that it can be repulsive. Fortunately for us on Earth, gravity only attracts, it never repels. So here you've got a negative charge and a positive charge. And again, if I make the charge smaller, the force, sorry, make it more negative, essentially making it bigger, the forces get larger. If I make the charge smaller, closer to naught, then the forces get smaller. And that's true for any charge. Make the charge bigger, the forces get bigger. You can see by the arrows or by the numbers. Make the charge smaller, and the forces get smaller. Of course, what happens here is if I make both charges negative, can you see the forces have turned around and they've become repulsive forces? That's something which doesn't happen with gravitation. The other effect is as I move the charges closer, the forces get bigger. As I move the charges further apart, the forces get smaller. So you can also experiment with different values using this great simulation. So there's a table at the bottom of page 67 based on Coulomb's law. And we've done the first row for you, but we want you to fill in the answers in the other 5 rows. So it's based on Coulomb's law. The equation is given to you there. Please pause or stop the video here for 5 minutes and try to fill in the correct answers. Again, I cannot stress enough how important this is. If you just look at my answers, you won't learn anything. So in this case, we're telling you what change there is in charge Q1, what change in Q2, and what change in R, the distance between their centers. What we want you to do is to say, what is the combined effect on of these changes on the force? So for the first one, if you double Q1, we'd say that F would become 2F. So please take 5 minutes to try to complete these, and then I will give you the answers. Okay, so I hope you've taken the time to try these. So let's have a look at them. Let's look at the second one. So if the only change is that Q2 is halved, there's no change in Q1 and R, then it's quite simple. F should become half F. And here are the other answers. Let's go through them. The third one, if you double r, this is similar to the very first one we looked at on page 66. Because it's 1 over r squared, 2r, when you square it all, becomes 4r squared. So the new force is 1/4 of the previous force. So those first three are quite simple. Now let's look at some combined effects. If Q1 gets 3 times greater and R gets 3 times smaller, well, making the charge 3 times greater will make the force 3 times greater. Making R 3 times smaller will make the force R squared 9 times greater. And 3 times and 9 times together, 9 times 3 is 27. So in fact, the force will get 27 times bigger. The fourth one, if the charges are doubled and the distance between is halved, that will have the effect of doubling the force. Doubling it again, that's 4 times. And then if R is halved, we see that the force will become 4 times as big. So it's 2 times 2 is 4 times 4 is 16 times the force. And finally, if Q1 is halved, Q2 is doubled, and R is made 3 times smaller. I hope you can see that these two changes will cancel each other out. So there'll be no effect when you combine these two, but having R 3 times smaller means that the force will be 9 times bigger. So it'll be 9 times the original force. Take some time to go through these with your teacher, have them explained to you if you're not clear about them. But Coulomb's law and Newton's law of gravitation are great favorites with examiners. Now let's go on to some real exam questions on the next 3 pages and give you a chance to try these and for us to mark them. Now, I hope that exercise was useful, but of course you're preparing for your matric exam. So let's look at some real ratio multiple choice questions taken from a number of matric final exams. These start on page 68. Turn there with me. So we've chosen 13 different ratio questions from the multiple choice sections of many previous exams. They cut across all subject areas. And if you can get on top of all of these over the next 3 pages, this will really help you. We're going to do them 2 or 3 at a time. So as always, I would like you please just to take 6 minutes to try to answer questions A, B, and C. Please circle what you think is the correct answer. Do it in pencil if you want. Make an attempt, and then I will give you the correct answer. So please pause or stop the video here for 6 minutes and try these 3 questions, A, B, and C, on page 68. Right, now that you've attempted an answer, let me give you the answers from the memo. Please don't be upset if you get them wrong at this stage. Rather get them wrong now and learn from it and get them right at the end of matric when it really counts. Right now, it doesn't count except as a learning exercise. The first one, which comes from the November 2016 paper, which we've labeled A at the top of page 68. This is from the photoelectric effect, which is question 10 in the long questions. There's the wavelength of a monochromatic, that's just a single colored light source P, is twice that of a monochromatic light source Q. The energy of a photon from source P will be what of a photon from source Q? Quarter, half, equal, or twice the energy. Now, the first step is to find the correct equation. And we need an equation which relates wavelength to energy. Because we're talking about the photoelectric effect, we look at the equations at the bottom of page 38. And in particular, we're going to choose this equation because it's got energy in terms of wavelength. H and C, Planck's constant, and the speed of light in a vacuum are simply constants, and they're not going to affect anything else. So we'll take that equation. We'll say, right, energy equals hc over lambda. So the energy of source P is a constant. We're just combining those two into one constant over the wavelength P. And we told here that the wavelength of P is twice that of the wavelength of Q. So I'm putting that in. So that'll give you half K over lambda Q. But that's simply half of the energy of Q. So our correct answer will be B, half the energy. You should know that the bigger the wavelength, the smaller the energy. Wavelength is directly proportional to frequency. Sorry, energy directly proportional to frequency, and energy is inversely proportional to wavelength. So the fact that P's wavelength got bigger should have told you that its energy would have got smaller and that the answer had to be A or B. In this case, it is B. Hope you got that right. Second question we've called B. It's from November 2015. You've got two charged spheres of magnitude 2q and q. They're placed a distance r apart. If the sphere of charge q experiences a force F to the east, then the sphere of charge 2q will experience a force. Well, do you remember when we looked at the simulation? And if you've forgotten, just go back in this video. What's really important is, according to Newton's third law of motion, the forces experienced by the charges must be equal and opposite directions, but equal magnitudes. And Newton's third law says these two arrows must be the same. They're just pointing in opposite directions. So of course, the answer here must be A. It doesn't matter which charge you're looking at and whether one is bigger than the other. They both experience the same force. So it's the same force F, but in the opposite direction. The original force F was to the east. The new one must be to the west. Bit of a tricky question there, because in fact the force doesn't change. And the third one in this first set is now, we've called it number C. It's from November 2017. This is to do with work, energy, and power. Notice we've had three different subject areas already. Person lifts a crate vertically upward at constant velocity through distance h. The person does work x on the crate in time t. The person now lifts the same crate vertically upwards at constant velocity through the same distance, but in time 2t. The work done by the person on the crate will now be. Now, this is again a bit of a tricky question. We're looking at work, energy, and power. So we go to those equations on our data sheet. Now, I want you to notice that the equation for work is concerned with force and distance delta x, but it is not concerned with time at all. It's only the power equation which is concerned with time, but this is not a question about time. So it doesn't matter how long the job takes. In fact, the work x will still be exactly the same. Now, you probably missed this, but if you look at the bottom of page 67, I put this note in. Look out carefully for questions where the final quantity is actually not affected by the changed variable at all. You will find a few of these on the next page. So I did give you a warning, but look out for this, that the answer doesn't always have to change from the original one, because in this case, work is not dependent on time at all. Only power is. So look out for these type. Right, let's look at the next two questions at the bottom of page 68. These two are about electric circuits and especially about the power dissipated in an electric circuit element. So first of all, once again, I'd like you please not just to wait for the answers, but stop or pause the video here for 4 minutes, 2 minutes per question, and try to complete these two questions on page 68. Have a go by yourself and circle the correct answer. Right, I hope you've taken time to answer these. Number D, when a resistor of resistance R is connected to a battery, the power dissipated is P. If the resistor is replaced with a resistor of resistance 2R without changing the battery, what will the power now be? Will it be more or less? Now, once again, where do we start? We always start by looking at the relevant equation. And we go to our data sheets and we're looking at power equations. And in particular, we want the relationship between power and resistance. Now, voltage doesn't change because the battery is the same. And we can see here that power is inversely proportional to resistance. So we expect that if the resistance gets bigger, the power is going to get smaller. So we expect answer A or answer B. So power equals V squared over R. Because velocity is a constant, you can just say K over R. It's inversely proportional to resistance. And therefore, the answer is going to be half P. If R becomes double, power becomes halved. Now, You can confirm these with the circuit construction kit. We talked about this in the Ohm's law and internal resistance videos, and I encourage you to use this fantastic PHET simulation to build a circuit and confirm these for yourselves. Another one on circuits, number E at the bottom of page 69. This comes from November 2018. You've got two circuits. You've got resistor X, which is one of two in series, and resistor Y, which is one of two in parallel. Now, all the cells and resistors are identical, but the circuits are not. They say the power dissipated in X is P. What is the power dissipated in Y? Now, once again, we need to look at our equations, and we need to remember that this circuit, the series circuit, is a voltage divider. So the voltage of the battery, V, is divided between the two resistors, each of which has a voltage of half V. In this case, it's not a voltage divider, so each resistor experiences the full battery voltage, V. Okay. So in this case, it's not R that's changing, it's V. Again, we're looking for a relationship between power and voltage, and we can use that one there. Because R is a constant, you might as well say power is equal to constant times V squared. So power depends on V squared. So we already expect that this power in resistor Y is going to be greater than this one here. So just substituting in, the power dissipated in Y is K times V squared, and that voltage is, so power in X is K times half of V squared. When you square it, it's a quarter of KV squared. So we can see that the power in Y is going to be 4 times the power in X, and the correct answer is D. Now, again, by anticipating the fact that the power should be more, it'll stop you from choosing the wrong answer, which could be P over 4 if you weren't careful. Now, once again, if you really want to get on top of this, take the time to set up the basic circuit in the PHET simulation. Remember the comment of the examiner. This comes from the national examiner, who says, although the principles of series and parallel circuits are taught from grade 9, the basic principles have to be revised and practiced constantly. The critical features of series and parallel circuits should be reinforced, and there was a direct suggestion that pupils and teachers should use PHET simulations. Why don't you take heed of the examiner and do just that? Right, 2 ratio questions to do with gravitation, F and G, on the top of page 69. As always, please take 4 marks here to stop the video, 4 minutes for the 4 marks to stop the video and try to complete these 2 questions before you watch the answers. So I hope you were able to at least attempt these. Let's look at the first one. This comes from June 2019, the mid-year paper. And in this case, they give you a graph. Please remember, we stressed this in the early videos. Interpreting and being able to read graphs is very important as an essential skill for matric. So they tell you that in the graph shown, there's a relationship between the gravitational force F and the distance from the center of the Earth. Now, you should know that that relationship is 1 over r squared. The magnitude of the force on the mass at a distance r from the center of the Earth is F. They want to know what will the magnitude be at point X there. Now, X relates to a distance apart of 6r. Now, because this one's perhaps a little bit more tricky, let's carefully go through the method that we taught you on page 66. Number 1, identify the correct equation. Again, it's Newton's law of universal gravitation. Secondly, remove all the variables not mentioned in the question. In this case, we're not concerned with masses because they don't change. So you can simply say F equals K over R squared, or F is proportional to 1 over R squared. Thirdly, substitute the new value for the variables which change. In this case, R became 6R. So the new force is K over 6R all squared. And of course, 6R all squared is 36R squared. And so you can see when we simplify it that the new force is 1/36th of the old force, or just F over 36. So the correct option is option D. Next question, G, top of page 69. The mass of an astronaut on Earth is m. At a height equal to twice the radius of the Earth, the mass of the astronaut will be. Now, data sheets, Newton's laws on page 38. Please notice that the equation for small g, the acceleration of gravity, which gives us our weight, is this one. But you weren't asked about the weight or the force on the astronaut. You were asked about the mass of the astronaut. And of course, your mass is the same anywhere in space. Mass is invariant. It's your weight which changes as the gravitational force of attraction changes. So in fact, the answer is still m, because your mass doesn't change no matter how far you are from the Earth. What would change is the value of small g, which depends on distance from the center of the Earth, and therefore your weight and the gravitational force of attraction. Now again, please note my warning at the bottom of page 67. Look out carefully for questions where the final quantity is actually not affected by the changed variable at all. In this case, mass is not affected by distance from the Earth. And again, please heed that warning. This is another example of that type of question. Two more gravity questions, H and I, at the bottom of page 69. Please take 4 minutes right now, stop the video or pause it and try to complete these two questions. Circle what you think is the correct answer. So let's get on to the answers. Question H, which comes from November 2019. The gravitational acceleration on the surface of a planet of radius big R is g. What will the gravitational acceleration be at a height of 2r above the surface of the same planet? Now, I've put the word above in red, so you won't miss it. Of course, that won't happen to you in the exam. So you need to learn to read your questions very, very carefully. First thing we do is look for an equation. Gravitational acceleration is this equation here. Small g, the acceleration due to gravity, equals g, that's just the gravitational constant, times the mass of the planet divided by the distance from the center of the planet. Now, in this case, of course, the mass of the planet is not going to change. The distance is going to change. What you need to notice is the question said 2r above the surface of the same planet. Now, 2r above actually means 3r from the center. And you need to pay attention to that so that you don't make a mistake. So if r becomes 3r, then g becomes g over 9 because r is squared. So correct answer there is answer A. If you said g over 4, you didn't read the question, and you were reading a height of 2r as if it was from the center of the planet, but it does say above the surface of the same planet. So please read these questions carefully. They can be tricky. Question I at the bottom of page 69. Gravitational acceleration on the surface of planet X with mass m and radius r is g. Gravitational acceleration on the surface of planet Y, which has double the mass and half the radius, is. Now, we should expect this to be higher because the mass of the planet is bigger, which will increase it, and the radius is smaller, which will also increase it as they are inversely proportional. This one's a bit tricky, so we'll go through our 4-step method from page 66. Number 1, identify the correct equation. Just like the last one, g equals gm over r squared. Number 2, remove all variables. Well, it's just g, which we're going to replace by a k, although we don't really need to. Number 3, substitute new values for the variables which change. So m became 2m and r became half r. Put those in brackets. Simplify the new equation, and when you simplify it and work it all out, you end up getting half km over r squared. That was our original equation for g, so therefore it's half g, and the correct answer is A. So when it's a little bit more tricky like that, it might be helpful just to go through that 4-step method carefully. So turning to page 70, We have two momentum questions, J and K, so quite different again. Again, because they're 2 marks each, please take 4 minutes to try to answer them yourself. Pause or stop the video and try to get your correct answers for J and K. Okay, let's have a look at question J at the top of page 70. 2 trolleys, X and Y. You're given this picture in the exam. Y has double the mass of X. They're held together by a compressed spring between them. Initially, they're stationary on a horizontal floor. The spring is now released and falls to the floor, so it pushes them apart. And you're asked, how does the magnitude of the momentum of trolley X compare with the magnitude of the momentum? Now notice magnitude. We're only looking at the size, the quantity. We're not concerned about the direction. This question from November 2019. Now, let's have a look at various quantities for these 2 trolleys with the different masses. The trolley Y will experience a force Fy pushing it away from X because of the compressed spring being released. It will experience a momentum Py to the right, and it will be accelerated to achieve a velocity Vy. Now, X will experience a force Fx to the left, which must be equal and opposite to Fy because of Newton's third law of motion. It will also experience a momentum Px to the left, which must be equal and opposite to Py because of the law of conservation of linear momentum. The difference will be that its velocity will be twice the velocity of y because it has half the mass. So m times 2v will be the same as 2m times v. So the correct answer here is it must be the same as the magnitude of the momentum of y because of the law of conservation of linear momentum. So this is another of these ones where actually the answer is the same as before and it doesn't change. Look out for them. This one is quite tricky. Number K, an object is dropped from rest and after falling a distance x, its momentum is p. It says ignore the effects of air friction. The momentum of the object after it has fallen a distance 2x is. This is from November 2019, and it's asking you to relate momentum to distance. Now, that's what makes it difficult because there's no direct equation relating momentum to distance. But let's go and look at our equations of motion. So we've got the equation for momentum, P equals mv, and we've got another equation which relates velocity to distance delta x. So we actually have to use both of these equations together. So final velocity squared is 2g delta x, and P equals mv. So P depends on velocity, and V depends on the square root of delta x. So we can say P depends on the square root of delta x. And you need to make that connection. So if the distance doubles, P is not going to double. Delta x goes from x to 2x. P goes from root of x to root of 2x, which is the square root of 2 times P. This one is a bit more tricky, so maybe listen to this again and take some time to be sure that you're clear. It all depends on this relationship between delta x and P. And finally, at the bottom of page 70, 2 electrostatics questions. I hope you've realized that the subject matter can change. And the important thing here in these ratio questions is manipulating the equations. It doesn't matter what the subject matter is. So we've got 2 identical spheres. And once again, please pause or stop the video here for 4 minutes. Attempt these 2 questions on page 70. Circle the answers you think are correct, and then I will mark them. Okay, let's look at the first one we've called number L. It's from November 2019. You've got 2 identical spheres. The picture was not given, but I'm giving you a picture carrying charges of plus Q and minus Q. Sphere R exerts an electrostatic force of magnitude F. They're brought into contact and then returned to their original positions. What is the magnitude of the electrostatic force that R exerts on sphere S now? Now this one is actually easier than it looks, because as soon as they touch together and electrons can flow freely between them, okay, plus Q and minus Q gives you a net charge of naught. So when they're removed again, they both have zero charge, and therefore the electrostatic force that either one exerts is just going to be zero. And that's because the positive and negative charges were cancelled out, redistributed when they touched, and so now there is no force between them. So look out for that one, please. The last one, number M at the bottom of page 70. Magnitude of the electrostatic force on charge Q1 due to another charge Q2 is F. Both charges are now doubled without changing the distance. What will the new charge be? Now again, this is a straight Coulomb's law example. Coulomb's law, F equals K, Q1, Q2 over R squared. We don't change the distance, which actually makes things easier, but the charges are both doubled. So therefore the force becomes 2 times 2, which is 4 times as much, quite a simple one. And the correct answer there is C. So that's all for this video on multiple choice questions, and especially the special ratio type questions. I hope that you understood my answers from A to M, but I really want you to get on top of the skills required and the method, because one thing's for sure, none of those questions will be coming up in exactly the same form in your exam, but they will come up in similar forms. And if you can understand the strategy, you'll be in a good position to answer any question that they throw at you. Thank you for watching. As usual, please stay connected for an inspiring interview with someone who's used the physics she learned to literally reach for the stars. Right, it's my privilege to be talking to Dr. Naomi Titus from the University of Cape Town. Hello, Naomi. Can you tell us a bit about yourself, where you come from, what you studied, and how you got to where you are now?
Okay. Hi everyone. So I am Naomi Titus. I just received my doctorate in astronomy, and it's a funny story. I also come from a rural town in the Free State where I grew up. And then through some encouragement from a friend, I ended up at the University of Cape Town, where I studied physics as my undergraduate degree. So you do a 3-year degree, and I did physics and I did astrophysics or astronomy. And the amazing thing is that, what we do in astronomy is all based on physics. So so I finished my degree. I got 2 degrees. I got one in physics and one in astrophysics. And then I continued my postgraduate studies. So from honors, master's, and PhD, focusing on astrophysics in particular, although everything is still based on physics.
Fantastic. And as you know, that this video is to prepare matric students for their paper 1 physics paper. Now, I believe you've had opportunities to work overseas as well.
Yes, so the great part of being a scientist or astronomer in particular is that you can really go all the way across the world and do studies there. So for part of my PhD, which is the last bit that you have to do before you become a doctor in a particular field, I had a supervisor at the University of Manchester in the UK. And so throughout my PhD, which is roughly a 3 to 4 year period, I spent 6 months there working with him and his amazing group. So it was really amazing to have time to also collaborate with other people across the world.
Fantastic. Naomi, we hear so much bad news about South Africa. And if you had the chance to work overseas, why on earth do you want to be back in South Africa doing astronomy?
Well, so the idea of astronomy in general is it's an international collaboration. So, you can be in South Africa, but you can still work with people from all the way across the world of technology nowadays. But in South Africa in particular, right now, astronomy is amazing here because we have the new Meerkat radio telescope, which is the most powerful radio telescope on the Earth at this point in time. And loads of international scientists are coming here to get data and to collaborate with us, because as South Africans, we have first right to this data. And even beyond, well, not beyond MeerKAT, but with MeerKAT, we also have an 11-meter class optical telescope, which is the largest one in the Southern Hemisphere. So here in astronomy, currently in South Africa, we are just doing so well and have all the instruments, and many people from across the world are coming to us to work with us and to just learn more things. So, yeah.
Well, that's fantastic. So it's not just the Rugby World Cup that we have, but we seem to be leading the world in astronomy as well. Naomi, obviously, you've had to work hard and persevere to get to where you are. Now, present matrics are really facing an uphill battle in being in Matric 2020. Have you got a word of encouragement for them in their studies?
Yes. No matter where you are, don't give up. When I started my matric here, I was doing very badly in math. I got I think my first test was a 30% average, and I was horrified at the fact that my math was that bad. But I had a number of bad teachers throughout the year. And then in my matric year, I decided, no, now I'll just, bunk down. And then at the end of the year, I managed to do well enough to even be allowed to go to university. And so if you are currently in matric and struggling, just put your head down and work hard. Bother your teachers so that they help you. They are there for you. And also just in terms of finances, if you're not sure where your world is going to go because your family can't afford to pay for university, there are lots and lots of opportunities, especially a funding agency called NSFAS, which works at all major universities, and they can fund you. So my parents couldn't afford my tertiary education. So my whole university life was funded by UCT and NSFAS. And at the end of the day, you do have to pay the loan back, but it's an investment to your future, and it is possible for you to study and eat and do everything with their help. So don't give up if you're struggling now, and if you're enjoying it also, just seize the moment.
That's a great message. Thank you so much, Dr. Naomi Titus from the University of Cape Town.